Alright, so starting but no part two of this lecture, right? The law of conservation of momentum, right? So we're starting from the principle. What's the principle that governs this, right? It states that for a system, right, of colliding bodies, right? So we should know collisions, right? Of colliding. Watch me struggle to spell the word colliding. Okay, lovely. Bodies, right? So for a system of colliding bodies, this total with the total momentum remains constant. Moment remains constant. So the momentum in and of itself just remains constant. That's all we're looking at. Yeah, right. So that's what we're looking at. Provided, right? The thing is now, right? We're saying that for a system of colliding bodies, the total momentum remains constant, right? But it needs to be right known. Like it needs, you need a note, right? Note provided that there is what? That no external forces are acting. Act on the system, right? So we're looking at that. We're looking at colliding bodies, right? So the physics of collisions are always governed by the laws of momentum that we have, right? And the first law that we discussed, right? So the first law there, the um Newton's first law, right? We have that there. We're gonna look at that. And we're gonna also look at Newton's second law. It's really governed by Newton's second law mostly, right? But we're gonna start with an equation to derive this, right? Which is our impulse momentum change equation, right? So remember our impulse momentum change equation that we were looking at, that we looked at briefly above, right? So let me just bring this up. Let's just make a small note of it, right? The impulse momentum theorem, right? It really just looks at this. F is equal to, right, our initial, what's our final momentum minus our initial momentum. Let me change that to a U, right? All over a period of time, right? And it gives us that the impulse, remember impulse is force times time. The impulse is going to be equal to mv minus mu, or really and truly just delta p, because we're recalling that p is equal to mv. All right, so that's really what I'm just gonna be referring to sometimes for a change of momentum. All right, but that's really just a theorem there. It should be fine. Just dropping that there just in case anybody can use it to like fill up some like holes in the information, right? So what we're looking at here now in a collision, right? So let's look at this. So we have a collision. Let me just not do that. Let me just do this. All right. Everybody's with me, right? I want everybody to just follow, right? We have ball A and we have ball B. All right. We're looking at the collision, right? An object experiences a force with a specific amount, right, of time that results in a change in momentum, right? So what we're saying is that let's say that A is experiencing. My apologies. A is experiencing a force, let's say of 5 meters per second here of velocity, right? Rather, right? That's the velocity. A is 10 kilograms. B is 5 kilograms, All right, we're looking at something like that. B is at rest, right? So we start off with some initial momentum of A. What would be the momentum of A here? Anyone? Momentum is equal to mv, right? Therefore, this would be 5 times 10, just
50
50
kilogram
what?
meters per second.
Kilogram meters per second squared. All right, we have that, right? So we have an initial momentum, right, before collision, right? So this is before the entire collision. I'm gonna be looking at stuff like that, right? When we look at questions, right? Of our initial momentum here, right? And then that resulting force acting gives the amount. Well, it tells whether or not we're speeding up the object or we're actually slowing down the object, right? In this case, we're acting in the x direction, the positive x direction. So we're moving to the right, right? So let's start here. Let's just do this concept here. This is before collision. I was gonna do this a little bit later, but looking at that, right? So that's object A's momentum here, right? Object B, now the momentum of object B here, this is PA. PB now would be the mass, right, times no velocity. Therefore, the momentum is 0 kilogram meters per second. All right. So looking at that there. So this is before collision entirely, right? Let's say that at collision now, or what we can call during collision, right? We have A and B touching, right? So there's some type of collision here, right? So there's collision. What's happening here, right? We're just looking at that general collision here, right? During the collision, right? So there are many things that can happen here. Many things that can happen, right? Either they move off together, so A and B move off together, right? Like touching each other, move off together, right? Or A can stop and then B moves off, right? Or something like that, right? So there are different ways in which a collision could end up, right? So they can like touch and then move off together, right? They can actually clink and then both roll back in the opposite directions, right? But we have something like that. But the major thing that we're looking at is the conservation, right, of the momentum specifically, right? So we're looking at the conservation of energy as well. We're gonna look at the conservation of energy as it relates to figuring out what type of collision it is. All right. There are different types of collision that we are going to look at, but just let's look at the analysis of the of conservation of momentum first. All right. So what we're saying is that momentum before in the system, right, must be equal to momentum after, right? So we're looking at that. So we want to derive the conservation of momentum, and then from there we'll go into the collision, right? And what happens to momentum before and during and after collision, right? So before we head into all of that, right, we have to analyze the conservation of momentum, right? So we can consider both objects, right? So we can look at this, right? So let's say that we have object 1, right, or object A rather, with a force of F1, right? So the impact of force F1 on object A, right, from an object B, right? So looking at this, an object B here, lovely, and it changes velocity, all right? So let's look at this. Wait, I want to draw this the other way around. Hold on, guys. Give me a moment. Let me draw this the other way around. What we're saying is B has an initial force, right? A has an initial force, F1, right? And what we're saying is that B is going to collide with A, right? or looking at that general system there, right? So B changes the velocity of A, right, from its initial velocity, right, to its final velocity, right? So let's say that we have a first velocity U, right, acting on the box as well, right? And then after the collision with B, so let's look at this. After the collision with B, so we have a collision there, right? We end up with a different velocity V. That's what we're looking at there. For the conservation of momentum, what we're saying, right, is that before and after are equal, right? So in order to get the conservation of momentum, right, we have to draw from Newton's third law, right, and the impulse momentum theorem up here. We have to draw from that. So we're going to be looking at something like this. So each time I'm going to derive something, I'm just going to write that in purple as my regular convention. So let's look at this, right? F1, right, in this case, is going to be equal to M1 V1, right, minus M2 V2 all over T, right? So considering two objects in collision, the impact force of F1 on an object A, right, from object B, right, changes the velocity of A. So looking at an initial velocity and a final velocity. So the initial velocity of A, right, is changed when B hits into it, right? And it creates our final velocity, right? So looking at something like this. So we have mass 1 with we have mass 1 and mass 2. That's what we're focusing on. Alright? So hold on. Let me just fix something here real quick. Let's describe mass 1 first. Let's describe the force of 1 first, right? So looking at this is the force of object A. Right? One object here. Right? So we have that there. By the conservation of momentum, we're saying that the force before must be equal, right, to the force after. Right? Let's look at this. For object B, right, F2 is going to be equal to M2, the mass of that object, the final velocity of that object, times the mass of that object times the initial velocity of that object. Right? U2, and this is all over T. Right? So we're looking at this, right? The force acting on object A and the force acting on object B, right? Force, remember, force is equal to mass times acceleration, right? Can anybody see where we get these equations from? Can we see that? Or do we need to go over it? I realize that I haven't stopped to ask how you guys are doing, so everything is fine here? Or do we need to go over how we got this? Yes. No.
Sir,
Sir, what?
go over.
All right. So what we're saying, we got this from. Let's look at this. This is from F is equal to ma. All right. F is equal to the mass times. Remember that acceleration is v minus u over t. So F is equal to mv minus mu over t. That's obvious now?
Yes, sir.
Alright, so let me just write here using F is equal to ma. We get that. Right? So we're looking at something like that. That's fine. Alright? So remember, right, we have one force there and the other force there, right? Now recall Newton's third law. because where objects are actually touching each other, right? They're being influenced. There's going to be a force acting on another object. Therefore, recalling Newton's third law, right? That every action has an equal and opposite reaction. We're gonna have F1 is equal to negative F2, right? Because if we're gonna have the collision or the interaction of two forces, right, in collision, right, we're going to have an equal and opposite reaction trying to occur, right, based on this system. If no other forces or no external forces are acting on the system, this will be true from Newton's third law. Following? Drop a one in the chat if we're following. If you're not following, you can ask a question. Alright, so we're following. Alright, so looking at that, right? So from this now, we know that F1 is equal to M1V1 plus, well, not plus, rather, it'll be minus M1U1, right? And that is over T. And then this is going to be equal to negative, right? Let me just put the negative, have these in brackets for mathematical validity, over T. Alright? So this makes sense, yes? So let's rearrange. Rearranging, we have what's going to happen for this rearrangement now, right? We're going to rearrange this entire equation up here. Alright? So what's going to happen after that rearrangement? We're going to end up with something like this. So first of all, right, t is divided on both sides. Alright? So t is acting on both sides. We know that this is in relation to some amount of time, right? So we can just remove those t's. Alright? Guys, can you hear me?
Sir, presentation stopped.
Okay, give me a moment. Alright, so hold on, let me fix this. Something just went completely off a while ago. Let me reshare. And let's get through this derivation real quick. Alright. So go ahead, what's the issue? Oh, I just saw that. Alright. Hold on. Let me bring up back the screen real quick. But I hope we can follow, because if what I realize that for a good amount of person, I'm not sure about you guys yet. I haven't been around you guys for too long yet, right? But math tends to be the major issue over the physics. So the physics is not really the issue. It's just like getting all these formulas, rearranging them, getting them to the right place, right? But let's look at this, right? So we have this equation here, right? Rearranging will have, let me just write the arrangement and let me see if you guys understand where the rearrangement came from, right? We end up with M1U1 plus M2U2 is now equal to M1V1 plus M2V2. Hmm. Can you see that? So time is dependent in the entire equation. We can't just remove time. That it really doesn't matter to us, right? And then we can look at this now. If we rearrange some stuff now and put all the initials on one side and all the finals on one side, we'll have this. Or we could write the initial momentum of A plus the initial momentum of B is equal to the the final momentum of A plus the final momentum of B. That is conservation, the law of conservation of momentum, right? Or we could have total initial momentum is equal to the total final momentum. That is the law. Alright? So I did all of that. Yes, I did all of that just to come back to the initial point that we discussed eons ago. Alright? So that is that. Any issues there? Alright, not hearing any issues from anybody. I'm not sure if I should be looking in the chat. Are there any issues in the chat that I need to deal with? Alright. But more or less that is that for the law of conservation of momentum. So we finished that. Alright, so how are we doing? How are we feeling, everyone?